Let's just get started now. So thank you for joining me on Saturday, on this afternoon. I wanted to give this talk for a long time. This is actually the third talk in a sort of series of talks that I've been doing over the last year, and they've been growing in like viewership. So thank you for coming. Seriously, it's a really good turnout. And the idea is really that some of these topics, they keep coming up when I speak with my friends. I keep having to, say something or the other about quantum computing when I'm with my friends because it's kind of the direction I'm heading in at the moment. And I wanted to do a talk to get some of the basics out of the way so that if we ever have like these conversations, then I should be able to say what a qubit is and you should know what that means. But also, apart from my personal goals to make sure my friends can understand what I'm talking about, I think it's really helpful to have a talk like this because you're going to hear about quantum computing in the news for the next 5 to 10 years. And when you read a news piece, to be honest, a lot of them say a lot of random things that aren't exactly true. And that's really why our talk today will begin with mathematics so that you all have some sense of what's happening like on the ground reality, what actually is a qubit, and what does it mean when people say things like a qubit is different from a bit because it can be both 0 and 1 at the same time. What does that kind of thing precisely mean? So we're going to look at things like that, but we're also going to, after I go through the mathematics, I have a few slides on the state of the industry, why we should be excited, things like that. And after that, I really wanted to leave it like as a free discussion. So if you have any sort of questions that have been lingering for a while about this technology or just from what I said, then we'll make that part of it free form. Can I just check I'm being heard, not speaking to the void?
Yes, all clear.
Okay, cool. So let me just explain the like 4 photographs here. The top left, so Jun Hong made a good point yesterday. Quantum computing is not like quantum laptops or something. It's not like personal computing. We're not going to see, it's not like quantum internet of things or something like that. It's really like supercomputers that are really just doing like input and output type, computations. We want to simulate some very difficult physics or, hopefully trying to solve some problems in like finance or optimization or machine learning. And we build this, huge setup, the top left image. That's a dilution refrigerator. It's basically a giant fridge that cools something down to absolute zero. Because a quantum chip, at least one manifestation of a quantum chip or a quantum computer, is just a simple silicon wafer, something like a normal chip, like your whatever Intel i7 and that kind of thing. But it needs to be super cooled for the quantum effects to start showing. So just want to get that very clear. That's what a quantum computer looks like. It's really expensive to build. All that shiny stuff is actually gold. It kind of needs to be gold. It has the right properties to make that kind of thing work. Now on the top right is like a rough image of what we're going to see today. So we're going to go from a classical bit, which is something that can be either 0 or 1, to a qubit, which has a whole sphere of possibilities. We'll see what exactly that means. Bottom left is an image. It's a quantum circuit. And the reason I put this here is because I just want to make you feel that quantum computing is like a real thing. Like when we do quantum computing research or we study these courses, like we have circuits too. We have rules for, what circuits are equal to what other circuits, what computations these circuits do. We haven't built any of these, like, well, not big enough, interesting ones, but we absolutely have this theory, which really makes it feel like a very real discipline. And the bottom right image is like your, you might think of it as a quantum Moore's law or something, like the number of qubits is doubling or whatever. But to be honest, this image is quite old. And in 2018, for some reason, they projected 72 qubits. We haven't even hit that yet. So it's 2021 now. We're hoping to get 128 qubits. I think Rigetti still wants to do, Rigetti wants to do 80 qubits this year. So there is hype around quantum computing and people promising a bit early. So I put this slightly dated image of the projection to give a sense of we're at 64 qubits today. We want to hit 100 by the end of the year, but that's already 3-4 years later than some predictions. So okay, let's get started. before that, I just want to say why I even bother doing this, why I stayed up late last night making these slides. I said some of it already, but I also really hope that someone here will take up my challenge and organize a similar talk on something they're working on that goes misunderstood a lot or is just really cool and needs to be shared. And I really like this quote. I hate everything that merely instructs me without augmenting or directly invigorating my activity. I think what's cool about quantum computing is that it really excites you and it makes you like wonder what more can we do with computers that no one's ever thought. And that's exciting. It's not so exciting to go into a field and just like memorize 10 different algorithms to do some kind of very specific thing. I mean, yeah. Ask yourself if the things you're learning are interesting. If they are, please come and share. Okay, cool. So let's begin. Now, I said that quantum computers are like supercomputers. And computing is actually many things other than just like supercomputers that are trying to solve very specific computational problems. Computing is also what we're doing right now, like interacting over this network, right? It's also when we play video games, that's also computing, or when we have like chips in our fridges or in our like automatic cleaning robots, like all of these things are also computing. But one perspective, and it's the perspective we will take today, is that a computer is just simply a machine where you put in an input, you say, here's a problem. It's kind of like a calculator, and then you want an output out of that. And what's interesting is much of computer science, much of like really business relevant computer science and theoretically relevant computer science can be put into this simple model. So when you do any kind of calculation, all kinds of companies are doing optimization, like optimizing your travel routes or your delivery schedules or your airplane schedules or your whatever, factory operations, simulations, like they do that kind of thing when they build cars, when they build planes. So a lot of computing really is something that can be fit into this input-output paradigm. And this will help us get to like what quantum computing is and what makes it special. But I want to highlight two things. When we have this kind of inputs being transformed into outputs paradigm of computing, there are like two things going on. We need some form of representation. We need to say, what is the scheme in which, because computers are automatic machines, right? You can't just tell them in human language, like, here's what I want you to do. So we need to think about representation. How do we make a very rigid, structured representation of our problem? And we need to think about how that representation gets transformed. So we're going to contrast classical and quantum computing on these two aspects, on how they represent and transform information. So I'm going to assume some basic familiarity with, computer science and mathematics, but there'll be like helpful things on the side if you've not encountered some of these concepts before. In a classical computer, pretty much any classical computer, at the lowest level represents information in two-level, like discrete, classical, we call them bits, right? It's just like, is this thing on or off? Is this thing 0 or 1? And bits are also in mathematics something like base 2 arithmetic. So our normal numbering system, we write with 10 digits, 0 through 9. If you had to write, and that's an arbitrary number, it could have been anything, it could have been 12, it could have been 60, it could have been 20, and all of those systems have been used before in ancient times, but it could have been 2. And 2 is the simplest because from an engineering perspective, you only need to make 2 different states work and you can put them together and you can represent any number. So yeah, I think generally this will be familiar, but if it's not, something like 110, a binary number, that basically means this is the 1's place, this is the 2's place, and that's the 4's place, 4 being 2 squared. And when you talk about sort of our normal everyday numbers, that's like the 1's place, 10's place, and the 100's place. But bits are really powerful because with bits, not only can you represent numbers, you can represent text. So this is roughly how we represent text in computers. We assign to every single letter of the alphabet a bit string, and it's of a fixed length, so we know like when to split them, and then we just do a mapping. But once you can represent text, you can pretty much represent anything. For example, if you have like a chemistry problem, that can be written down in text in some way. So that can go into your computer. And if we have, images, audio, like anything really, it seems like you can represent everything with bits almost. Okay, so that should be pretty familiar to most. But let's just like step back for a moment and think about what a bit actually is. And I think an important thing to realize that this slide is the wordiest and the most boring in the whole thing, but it's like also the most philosophical. A bit is kind of like it's a physical system upon which we put an interpretation, right? So if you've ever come across things like people building whole computers in Minecraft, or people building whole computers out of domino, well, not whole computers, but people building like, simple adding circuits using domino lines or bubbles that flow in a tube. What's really important to note about bits is that it's just some system that can either be 0 or 1. And that's an interpretation you put upon it. There's no physical reason why computers have to be electronic circuits. We just use electronic circuits because it's easy to make them. We found a trick that works, like transistors. And so it's easy to pack lots and lots of components onto small devices. If we used dominoes, we'd have to line them up again every time. If we used, well, Minecraft is a simulation inside of a computer, so that's really slow. And yeah, people used to try to build computers like mechanically with like gears and things, but today we use electronic machines. But there's nothing essential about that. What a bit is, it's a system that it has two states. It doesn't move when you don't change it. It just stays there. If you set a bit to 0 and you come back the next day, hopefully it's still 0. That's what you need it to be. And you can read it because you need that for computation. You need to be able to test conditions, and yeah, you can change your bit. So, all right. And how do we generally like transform bits? Remember, we were talking about computation as representation and transformations. How do we transform bits? So, we have logic gates, and I'm going to assume this is like, if not something you've seen before, and, or, and not are just like the English words. So if you have a bit coming in to the NOT gate, it gets flipped. And then the AND gate makes sure that both the inputs are 1 before it outputs 1, and so on. So at the lowest level, even though computers we've talked, like those who came for the previous lectures, we've talked about like Turing machines, finite automata, all these kinds of things. But at some level, everything can be, when you think of like physical realization, everything can be boiled down into bits and logic gates. Even Turing machines, even all of that, it just comes down to these very simple components that we put together, and everything we're doing right now, is going through millions and millions of logic gates to make this all happen. So what's really cool is now we're going to see quantum bits, how they work, and quantum logic gates. And the mathematics is going to be much more involved. So let's much more, but not so much more to be scary. So let's see. But firstly, why even go there? Like I already said, you can represent almost anything with bits. Like, why should we bother, going to quantum bits? And there's a quote that you can't give a quantum computing talk without. Nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. Feynman was a physicist, Nobel Prize winning, if you haven't heard of him. And he was working at the time when sort of quantum theory was just coming into its own, and he solved some of the problems in it. But one thing he realized, as someone who was quite interested in computer science, was that the kinds of problems he was working on, the kinds of physical systems that he was working with, would pretty much never be simulated on classical computers. We'll see why by the end of the talk. But it has to do with the fact that quantum systems, if you tried to represent them somewhat, like if you just tried the naive way, it takes like an exponentially large number of bits to represent a quantum system. So if you double the size of the quantum system, or actually if you just add one more like piece to the quantum system, it doubles the amount of like representation, the number of bits you will need to represent it. So we'll see what that means. But basically, it seems completely impractical to simulate quantum physics and some of these like interesting systems which chemists care about. Perhaps some people in biochemistry might care about someday if the quantum computers get big enough, and certainly physicists care about this. You need to make computers that fundamentally know quantum physics in some way, like they work already with quantum physics, if you want to simulate them. And at first that might seem like, okay, but that's cool and all, but I'm not really interested in simulating physics. And to be honest, neither was I when we came here. But later people found that not only can you simulate physics using quantum computers, you can do all kinds of cool other things. And one of them is like especially important, which is you can factorize large numbers very efficiently. So we'll get to that. But that is firstly, I want to make a clear point. That is not like a physical problem. You wouldn't think that going into like quantum physics would suddenly allow you to factorize numbers. So I mean like prime factorization, like 15 is 3 times 5. So it was really surprising that you could do that. And because you can do that, lots of people have been inspired to think, what else can we do with quantum computers? Not just, simulating physics, which was the original intention. It's still one of the biggest like expected business drivers, like business value of quantum computing, but we hope to get to other things as well. So again, we're thinking about computers as input-output machines that represent information in some way and transform this information. And now we're going to enter the main part of this talk, where we talk about how exactly information is represented in quantum computers and how it's transformed. Before I go there, does anyone want to clarify something about classical computing, or just if there's something big I missed? Okay, I'll give it another second because this always happens in lectures where it's like you pause and then just when you start, the person's finally got the confidence to ask the question. Okay, all right, let's go. So firstly, I need to give you some sense of what kind of system ends up being a quantum bit, because the kind of systems, I didn't give too many examples earlier, but what I said about bits kind of connotes something that it's very, it's a very everyday type of object, like a light switch. It's either a 0 or a 1, and it's going to stay in that position. And I'm going to assume everyone's seen like a quantum physics meme. So you've heard of things like something like Schrodinger's cat being both dead and alive. You've heard of things like entanglement, like two things that are correlated and whatever. So when does that happen? Because light switches clearly don't, go into superposition. We're not talking about when you put your light switch like perfectly halfway. That doesn't count. That's just sort of outside the model of the light switch. The light switch is just either 0 or 1. Okay. So when does a system get into this kind of weird quantum behavior? And one example, just so that you have something in your mind. This is not the only example, but it's, I think, the easiest one to get your head around is if you have an atom. Yeah, this is an atom. So those would be protons and neutrons in the nucleus. And you have these like electron shells that you might have like studied in chemistry. And then these are like, you can imagine in the electron shell, you can imagine that there's like an electron that kind of lives there and whizzes about. But what happens sometimes is if maybe a photon hits your atom or some beam of energy comes in, that electron might absorb that energy and get excited and enter like another electron shell of a higher energy. So I'm not the authority on physics, and even in this Zoom call, but roughly I understand that's how we can model electrons and what they do on these like in an atom. But what's really interesting is that whether or not an electron is in this shell or in the shell above it seems not to be something like a light switch, which has a definite answer that it's just either in the 0 shell or in the 1 shell, in the ground state or in the excited state. It seems that there are certain things you can do, appropriately shine the right kinds of light, put it in the right kinds of magnetic field and whatever, that would lead to a state where, let's say you did this to like 100 different atoms, and then you try to ask the atom, so that's doing another physical procedure. So where is the electron? Is it in the excited state or in the ground state? And what you would find is that it's kind of, a random probabilistic event. It doesn't have a fixed answer. And the mathematics that best captures the behavior of this is quantum mechanics, which we're going to see. So I think of quantum physics, quantum mechanics as something that people say it's not intuitive and this kind of thing. I think of it as the best like mathematics we can come up with that properly captures this sort of weird behavior where something isn't properly in one state or another. And the real like quantum physics, when physicists do it, isn't about like two states. It's we're going to talk about two-level systems, like they're bits. But when physicists do it, they have like, it's not even like they have n levels. They have sort of an infinite continuum of different states and so on. But really, let's just focus on the core ideas of superposition, entanglement that you hear about. They appear already when we are in this like two-level system regime. So basically, what I'm saying, and by the way, if I'm like completely in error, just like Raj, just come and correct me. But I think what's going on is that an electron is, it's unclear where the electron is. And the best mathematics to model it isn't simply to say, it's here with some probability and here with that probability, but it's slightly something more than that. And we're going to look at that mathematics. So this is the kind of system that ends up being a quantum bit. So for example, when we plan to build these quantum computers, we're actually going to try to trap an atom or an ion or something, using all kinds of cool physics, magnetic fields and lasers. And we're going to literally trap one atom, and we're going to send energy to it to change the state of its qubit. Yeah, that's like what's at stake here. We're going to take computing so far that we need to like put all fundamental particles at work to do computing. All right, so let's see. So we all know how to describe like what a bit is doing. A bit is either 0 or 1. That's it. You just point at it and you say the bit is 0 or the bit is 1. How do you describe the state of a qubit? As I said, we can't just describe it as being, in the ground state or the excited state. We can't just say this qubit is in the state 0. There's the full description of what a qubit is like sort of up to requires this bit of mathematics here. So on the right-hand side is a refresher on complex numbers. If you haven't been studying maths for a while, complex numbers, like just remember I is like the square root of -1, and complex numbers are a real plus an imaginary part. But I'm not gonna look into that now. And so when we want to talk about what a qubit is doing, it's very simple. It's just two numbers, two complex numbers. And so we can say the state of a qubit is described by a vector. And we just put a small constraint on this vector that it's normalized. So its length is 1. Okay. And if you just need a refresher on what this means, if you take a complex number, you can kind of draw it on a XY axis, and the length of this, that's what this means. So, okay, the sum of those lengths need to be 1. So that's just a constraint we put on it. But yeah, the state of a qubit, what a qubit is up to. If I have to say, so what's the answer to this computation? What is the state of my qubit? Actually, that's not quite right. But let's say I'm doing some computation. I say, okay, I apply these gates and this and that. And so my friend asked, okay, so what state would the qubit be in after applying this procedure to it? That's the kind of thing I'm talking about. Whereas a bit, we might say, okay, the bit is just 0, and then after I apply a NOT gate, it becomes 1, and then I pass it through an AND gate, this and that, and then over here I get a 1 or a 0. It's very simple to describe the state of a bit, but to describe the state of a qubit, you need to give this two-dimensional complex valued vector. Right? Is that clear? Like, does anyone have any questions about that?
Is there like 4 numbers in total then?
Yes. So that's a very good question. So one thing you could say is, okay, so that's basically 4 numbers, because you could think of it as A0 plus B0I and A1 plus B1I. And so these 4 numbers, A0, B0, A1, B1, you could say that the state of a qubit is 4 real numbers rather than 2 complex numbers. I will just say that I'm doing some simplifications here, but there's a reason we prefer this, firstly. And another thing I'll say is, in truth, actually, you only need 2 real numbers. I won't expect you to understand this right now, but for those who are sort of more practiced with mathematics, the idea is that when you have 2 complex numbers, and when so that's 4 real valued like numbers, there are 2 constraints as well that go upon qubits. One constraint is this one that I presented. And so when you put on this constraint, it means you don't have to save one of the numbers, because you can derive it once you know the other 3. And there's another constraint which has to do with, yeah, I won't mention it that now, but there's another constraint which when you consider that, you will realize that you actually only need two real numbers. But for sort of simplicity, that last like 30 seconds of explanation, don't worry if you didn't catch that. For simplicity, we're going to assume that it's two complex numbers. Any other questions? Okay, so that's how we describe state of a qubit. And we are quantum physicists. We have our own notation for some reason. I mean, for a very good reason. It helps us in our computations. So we write our vectors like this. We write the zero component. So I'll just go back 1 second. And so we have two components, right? A vector is just basically a list of numbers with an order. So Z0 and Z1 are our components. And we write it this way, okay? You can think of this as the vector 1, 0, and you can think of this as the vector 0, 1. So this is really just the same thing, okay? That's just the way we choose to write things. And when we write it this way, we can talk about these two components, these complex valued parameters that describe the state of our qubits. We call them amplitudes. And we say these amplitudes are the amplitudes corresponding to certain states. So corresponding to state 0 or corresponding to state 1. For example, if we go back to this, we could say, let's say for a particular atom that we've prepared in our lab, we could say that the amplitude corresponding to the ground state is so-and-so, and the amplitude corresponding to the excited state is so-and-so, and that fully describes what our qubit is doing. Okay, so this is just, I've just rewritten it. There's nothing that's happened here. But now you can already begin to get your first much needed clarification about quantum physics. I think, this is something that really bugged me when I was trying to get into it. I think Schrodinger's cat is a very bad thing that makes people confused. It certainly made me confused, because I did the whole quantum information course and I was like, that's great, but I still don't understand what Schrodinger's cat, well, how is it dead and alive? I don't think that's a good way to say it. I think what's a good way to say it is that you have this cat and the amplitude corresponding to it being dead is 1 over square root of 2. And the amplitude corresponding to it being alive is 1 over square root of 2. If you're wondering why it's 1 over square root of 2 and not half, it's because of this constraint. We need the squares of the amplitudes to add up to 1. Why do we need that? Anything that doesn't exactly make sense seems like a bit enforced. It's just because the mathematics works out more beautifully if we do it this way. Not in every particular case, but in overall. Okay, did that help anyone? Does someone feel like they understand a little bit more what's happening with Schrodinger's cat right now? I should have asked the question in negative. Who is still confused about Schrodinger's cat? Okay, let me just try to explain one more way if someone's being shy. So I'll revise what Schrodinger's cat experiment is roughly about. Suppose you had a cat in a box, and there was a genuinely random, quantum mechanically random event that takes place in the box. And based on whether that event came out to be, let's say, a 0 or a 1 outcome, it's an event that can only be 0 or 1. The cat either is exposed to cyanide and dies, or nothing happens. And this is a thought experiment, and the idea of the thought experiment is to communicate what quantum mechanics is about. And people will say Schrodinger's cat is, until you open the box, it's neither, you can't say it's dead because you don't know what the quantum event did, and you can't say it's alive because you don't know what the quantum event did. So the only thing you can say, so goes the explanation, is that Schrodinger's cat is somehow both dead and alive. And when you open the box, it becomes one of those possibilities. Until you open the box, it's somehow both. I think that's confusing. I think the truth, which is, requires 2 slides of mathematics, is that we should model Schrodinger's cat as having 2 different amplitudes corresponding to its 2 different possible states, there's an amplitude of 1 over square root 2, that corresponds to it being dead, and an amplitude of 1 over square root 2 corresponding to it being alive. And like just the next slide, we will see how measuring qubits works. So we will see what happens to these amplitudes when you open the box. And by the way, this is what superposition is in quantum computing and in quantum physics when we consider two-level systems. It just means that you have some system that instead of being entirely just an alive cat or entirely a dead cat, it is best modeled as having amplitudes corresponding to those different states, which it kind of feels like probability distributions, but it's not exactly probability distributions, because it can be a complex number, first of all. And secondly, the full physics only works out when you treat them properly as complex numbers. So they're amplitudes, not probability values. So my explanations have been sort of at multiple levels, because I know there are some people in my talk who are doing maths every day, and then there's some people who are maybe doing like a business degree. So whatever you're like comfortable with, just take the explanation you're comfortable with for now. Okay, any questions? Okay, cool. So what happens when you measure a qubit? Firstly, what does that mean? It roughly just means you do something to get the answer. If you're like a human, you do some procedure in the lab and you can like ascertain something, like opening a box to see if the cat is dead or alive, or doing some procedure in the physics lab to work out whether the electron was in the ground state or the excited state. It's weird that a physical theory involves like humans interacting with the system to like come to know what it is. It's not really about humans, but as a first like approximation, you can think of it as, yeah, to measure a qubit is to do some procedure to like figure out what it's actually doing. That procedure could have happened without humans, like if a light, if a light beam were to come and hit the atom in question, that could also constitute a measurement depending on what's going on. Schrodinger's cat is a bit confusing because actually the cat is, genuinely it is actually just dead or alive, because after some time you can start smelling a dead cat in the box. Opening the box isn't very special. So, but with like molecules, yeah, there seems to be, things that are sort of in superposition, they haven't been measured. And then when you do a certain procedure, or when some noise from the environment hits your atom, then it gets observed, it gets measured. And so what happens? What happens is that it collapses to one of the two states. This is the weird thing about quantum mechanics, is that the true mathematical description is that you have this vector that explains what it's actually doing. But the moment you look backstage and you see what's going on, they're going to quickly collapse to either being in the ground state or the excited state. Whatever your two-level system is, the 0 state or the 1 state. If you open like Schrodinger's cat, the idea of the experiment is that the cat is somehow in this weird mystical, quantum superposition, and when you open the box, it collapses and now it's dead. You've sort of brought its death to reality. Before that, it was just like in a superposition. And there's a rule that governs the probabilities of these events, because while it's random, we can still create a physical theory that explains like the probabilities. And that's by the way, like been a big thing for physicists, because historically the idea of physics, our aspirations were that we could come up with physics that completely model reality deterministically. Once you know the current state of the universe, the laws will determine what the universe is going to be doing in the future. But what we've now had to accept is that simply some physical theories can't aspire to that goal. And the most we can aspire to is to know probabilities of events. And so Born's rule is the answer to this in this case of measuring two-level systems. The probability of your two-level system being in the 0 state, so being in this state, is the square of the absolute value of the modulus, I think, the square of the modulus of this complex number, right? So to give an example, the probability of our cat being dead when we open the box is the square of this number, which is half. And of it being alive, it's also half. So just this is by the way, why we had that condition earlier, that the sums of the squares need to be 1, because this gives us a well-defined probability distribution. To be a probability distribution, all the outcomes need to have probabilities that add up to 1, because the probability of something happening is like 100%, it's 1. So that's what this condition guarantees. Okay, so let's do an exercise. Can we work out for this second cat, so it's a slightly differently prepared Schrodinger's cat, what is the probability of it being alive when we open the box? And let's like do a thing where don't answer if it was really easy for you to get the answer. Someone want to like volunteer to talk through it?
Wait, for cat 2?
Yes, for cat 2.
I'm gonna guess 2/3.
And so okay, so how did you come to that?
1 minus the square of the other thing, which is the probability of it.
Right. So okay, so in this case, yeah, you could look to the other side because this is an easier number to square. So specifically to square the modulus of, because we have to do this. But yeah, the probability of it being dead is 1/3. So whatever is going on here, if this is a well-defined quantum state, then this should square to 2/3. And so the probability of it being alive is 2/3. If you didn't see this, or if this number was quite complicated, what you would do is you would go 1 plus square root of 3, and then this operation finds the length of your like complex number, right? In that representation, and that length is how should I explain this? Okay, so if we drew this out, this would be like 1 over square root of 3 plus I over square root of 3, right? That would be the position of this complex number. And so we have this like right angle triangle. I feel like this explanation, if you didn't get it, this explanation might not help anyway. But anyway,
I think you can use Pythagoras, right, for the top part.
Yes, that's right. So this would be a Pythagoras situation. So you got 1 over square root of 3 squared, that'll be 1/3, plus 1 over square root of 3 squared. Sorry, this is like I over square root of 3, but we don't consider the I because I'm just going to go back to this. We take the complex coefficient, sorry, the imaginary coefficient, but the thing that multiplies with the I, and we just take that and plot it on this. I wasn't pointing to anyone. So yeah, this will be our basically 1 over square root of 3. This will be 1 over square root of 3. So this length, because this is a right angle triangle, will be, its square will be the square of this plus the square of this, which is 2/3. And we're just interested in its square because that's what we want. So the probability of the cat being alive is 2/3. So this cat's doing better than Schrodinger's normal cat. But this is how we talk about qubits. So suppose you did some computation and the final state of that computation was, that the qubit will be in this state. And now just before you can output your answer, you need to measure, because without measuring, you know nothing. You just sort of, the state's doing its own thing. But when you measure, you want to get the outcome. So this could be like a possible, obviously if it was just one qubit, we could like completely do the mathematics by hand. So it might seem like, why are we even measuring it at that point? But let's just say, you couldn't simulate like one qubit by hand. So you have this qubit, it's described by this thing. And then now we want to know what happens when you measure it. We have to use Born's rule. That's the idea. Okay, does anyone have any questions about Born's rule? Or any questions so far? Is this talk not what you expected? What I'll say is that now, when you read a news article about quantum computing and it says, quantum computers are amazing because they can do things in parallel, they can have, states being both 0 and 1, what they actually mean by that. What they actually mean is these different states have amplitudes assigned to them. And when you finally read the answer out of your computer, you're going to get one of the answers at random depending on these coefficients. And in particular, I would say that the whole point of quantum computing is somewhat to, produce a state such that your correct answer is measured with a high probability. So it's kind of like you want to save Schrodinger's cat. Schrodinger's cat you want him to be alive, and you can think of that as you want the computation to measure to have the answer to your question. So you do some stuff which we're going to talk about, how you actually transform a qubit. But now we know what the state of a qubit is, and now we know what happens when you measure it. At the very end, you want the probability of your desired outcome to be high. And that's roughly how quantum computations are designed. Okay. Before we talk about how we evolve qubits, actually, this is quite an important point. So when we have individual bits, and then we use them to make a string of bits, we just sort of put them next to each other. You can sort of, suppose we have 4 bits in the state 1100. Well, that's just, the first bit is in state 1. I'm done explaining it. Let me put a nice semicolon and move on to my explanation of the second bit, which is just in the state 1. Okay, I'm done explaining that. Let me move on to the explanation of the third bit. The third bit is in the state 0. And I'm done explaining that. And let me move on to explanation of the fourth bit. The fourth bit in the state 0. Now, why did I explain that so slowly? It's because you can't do that with quantum bits. You can't just say that, okay, I've got like 100 qubits, and my first one's doing this, my second one's doing this, my third one's doing this, and so on. Quantum bits can get entangled. Qubits, like the qubits and quantum bits, they're the same. Qubits can get entangled, and when they get entangled, what it is that sort of allows them to get entangled is this slide here. What I'm explaining on this slide is that the state of multiple qubits cannot be described just by first describing the first one and then describing the second one and so on. Multiple qubits are more than the sum of their parts, okay? And so let's take the example of 4 qubits. If you have 4 qubits, what you might think, if you didn't know about the rule I'm explaining here, is that, okay, each qubit needs 2 complex numbers, so 4 qubits would need 8 complex numbers. But what you actually need to describe the state of 4 qubits is 16 complex numbers, okay? And in general, the rule is if you have a state on n qubits, you need 2 to the power of n complex numbers to describe its state. So that's why when we had 4 qubits, we had 2 to the 4, 16 dimensions, 16 complex numbers. Now, this is really interesting because it means that if you build a 1,000 qubit quantum computer, something that humanity should really do by this decade, if not in the next 3 years, then you would need 2 to the power of 1,000 complex numbers to classically explain and simulate what this quantum computer is doing. And if you're more familiar with base 10, that's about 10, like 1 with 300 zeros. That many complex, it's more than the like particles in the universe and all those numbers you hear. It's more than, if you fill the universe with lead and every particle is like the universe and it's filled with lead and the mass is that whole, like, come up with a story, just don't make it too crazy. And yeah, it's going to be 10 to the 300 is going to be bigger than that. So this is where the power of quantum computers comes from, because once you make 1,000 qubits, in fact, once you get to 100 qubits, you already have something so massive, computationally massive, like so much is going on in terms of information representation that you could never write this down in any other way classically. And this is what Feynman was talking about when he said, nature isn't classical, damn it. So if you want to make a simulation of nature, you have to make it quantum mechanical. It's because a quantum computer can represent, in a weird way, it's not actually representing all of them. Like you can't ask the quantum computer, give me like the amplitude for your 922nd state, so it's not representing in the usual sense that you can just ask it like a database. So what's that number? It's not like crazy memory. We're not building a computer that can, it's not like we're going to replace gigabytes and terabytes with giga quantum bytes or something. This isn't memory in the sense of that we're used to. but it is some kind of memory. It's slightly deficient, but because there's so much of it, it's still really exciting that we have these systems that are so difficult to simulate, but they do map onto some things in reality, like physical systems, which we might want to simulate. And so this is roughly where the power of quantum computers comes from. But what does it mean? What does it mean to have these 16 numbers? What do the other numbers represent? So let's look at that now. And again, we're going to dive into a little bit of mathematics. So this is just a very simple operation. It's called the tensor product. If you have two vectors, A1, B1, tensor product, A2, B2, this is how you evaluate its tensor product. You take the first number A1, and then you multiply it with each of the components of the second vector, so A1, A2, A1, B2. And then once you're done doing that, you take the next one and you multiply it with each of them. So B1, A2, B1, B2. Okay, so very simple, syntactically defined operation on two vectors. And if the vectors have different sizes, you can still take their tensor product, take A1, take its product with A2, and then with B2. So it goes like that. And then B1 goes with A2 and B2, C1 goes with A2 and B2. So again, a business article won't show you this, and it can't afford to, but I really think this is a simple thing to get your head around. And now you're going to come to understand why the state of multiple qubits is, more complex than just describing each one independently. So just some examples on this notion of tensor product. So if we take the vector 1, 0, tensor product with the vector 1, 0, we're going to go 1 times 1, 1 times 0, 0 times 1, 0 times 0. And if you evaluate all that, you get 1, 0, 0, 0. Okay. You can always take the tensor product of any two given vectors. But if I give you a vector, it's not necessarily going to be the tensor product of some vectors. So this is an example here. You can't have the vector 1, 0, 0, 1 written as the tensor product of two vectors of two dimensions. Why is this? Does anyone want to try?
Because the only two numbers that multiply will give you 1 is 1. So everything has to be 1.
Okay, you're on the right track, but there are many ways to get A times C equals 1, like -1 and complex numbers and that kind of thing, or even 2 times half. So, right. So I think your idea was that, okay, if you evaluate this tensor product, AC, AD, BC, BD, and then if you compare the first component here with the first component here, which would need to be equal for these vectors to be equal, you would get AC equals 1, which means, I guess, A and C equals 1, but that's not right, because you could have 2 times half, for example.
But they can't be 0.
That's right, exactly. So what you get, okay, let me explain that again. So when you evaluate this tensor product, you get this vector, which I've written a bit shabbily, but what we need is that each component is equal, right? Two vectors are equal if each of their components are equal. So we would need in particular that AC is 1, we would need AD is 0, we would need BC is 0, and BD is 1. Now, if we look at this first condition, this one, if A times C is 1, neither of them can be 0, because if it were, then that should be 0. And if B times D is 1, then neither of them can be 0. So none of A, C, B, and D, which is all of them, A, B, C, and D, can be 0. But we have these two other equations that also need to be true. And the only way that AD can be 0 is if one of them is 0. Okay, so if you haven't seen a proof like that in a while, I hope that wasn't too difficult. And the idea is simply, a vector like 1, 0, 0, 1 cannot be factorized, cannot be, I say this is like a word that I'm just using. It cannot be split up into two vectors. Okay, and this is going to be an important thing to understand. So if you didn't get it, let me explain it again. If anyone has a question about this.
Wait, why can't they be 0 again?
Okay, so if we have A times C is 1, we have two different numbers, we multiply them and we get 1. Well, if A was 0, let's just say, what would C need to be for this equation to be true? Right, that's like multiplication. Does that make sense?
It's impossible.
If you don't get it, like you can
Oh,
say
okay,
like,
got it. Oh,
right. So yeah, so if AC is 1, both of them must be non-zero. Similarly, if BD is 1, both of them must be non-zero. So A, B, C, and D must be non-zero. But that was just us accounting for the first and the last components. When we turn to any of the other components, we see that AD is 0. So one of A or D must be 0 for that to work out. You can't multiply two non-zero numbers and get 0. All right, so this vector is going to show up and it's going to be quite important. But so far, in these last 2 slides, we've just introduced a new piece of mathematics, which is just going to be essential for us to talk about what we're going to talk about. And it's very simply this thing called tensor product. You take 2 vectors of different sizes, you make a larger vector. By the way, the size of the larger vector is going to be, the products of the sizes. So this was the 3-dimensional, this was 2-dimensional, this one is 6-dimensional, because you go like every pair like that. So, okay, that's good. This is good. And then we said one important thing about the tensor product is that you can always take the tensor product of 2 vectors, but if you have some vector, it's not always going to be the tensor product of some smaller vectors. Cool. So now we can talk about what happens when you take multiple qubits together. So the truth is, I said that the state of multiple qubits can't be described by enumerating what the first one's doing, what the second one's doing, and so on. But actually, some of them can be. Those are called product states. Okay, so if I have 10, Schrodinger's cat that were produced like independently from one. Okay, here I've got the example of 2, so let's just focus on that. So I independently prepared 2 different quantum states. You can think of them as cats. You can think of them as atoms where the electron is in some state. You don't know which, or like the quantum description of it, but you don't know exactly where it is until you measure. If you have these just like 2 completely separately prepared quantum states, then you can describe what the first one is doing, followed by what the second one is doing, right? And that's called a product state. I'll come to why it's called product state, but for now, I just want to make that point really clear. So some quantum states, if they have nothing to do with each other, suppose 2 different experiments, one being done at NUS, one being done at NTU, they're both preparing, Schrodinger's cats for a quantum conference. Because they have nothing to do with each other, those cats they live on their own, and what they are doing, if you want to describe what both of them are doing, you can first describe what the first one's doing and then describe what the second one is doing. But if you want to talk about, let's say, I have 2 cats and I'm doing some experiment where I want to prepare both of them in an entangled state, so a non-product state, it's possible for me to do that. And in particular, I'll give this example. It's possible for me to prepare 2 cats in this state here, which is an entangled state. It's actually, if you don't see it, how this is the same as the vector in the last slide, I can just factor out the 1/2. So this is basically the same state, the same vector as this one. I just need this 1/2 so that we can satisfy that. Remember the constraint that the squares of the moduluses of the amplitudes need to add up to 1. So I need to normalize my vectors. So you don't have to worry too much about this for now. It's like basically the same mathematics as the last slide. So I'm just going to assert, this is what physicists would guarantee you. You can actually prepare 2 quantum states in this state. So the full description of what these 2 quantum bits are doing, you can't describe it any other way than by saying that both of them together are in this state described by this vector. Okay. In particular, you can't say that the first cat is doing this and the second cat is doing this. You have to, if you want to give a full physical description of what they're doing, you have to give it in this way. And so if you had, let's say, 100 quantum bits, qubits, and you wanted to describe the state of what they are doing, you imagine a 2 to the power of 100 dimensional vector, which is basically the only way you could describe what they're doing, assuming it's not like a product state where you can separate all those descriptions. I think that might have been a bit fast, so please ask a question. We can go from there. Do I have a slide? Yeah, I have slightly more on that. If a question comes up, say it. Like be preparing it. So again, honestly, this is just my view of entanglement. I haven't really heard anyone explain it this way, but this is how I explain it to myself. So if you have 4 bits and you want to describe what they're doing, you can sort of use these like semicolons. Think of a semicolon as like as the grand pause you take between every description, right? So what are 4 bits doing? They're doing 1, and then the second one is 1, the third one is 0, and then the last one is 0. What are 2 qubits doing? Well, if there are 2 qubits that haven't been entangled, they've been prepared completely separately, then you can also separate their descriptions. And the tensor product here acts as the semicolon in a sense, right? So what is the state of these 2 qubits? Well, actually, you can take, so suppose we took these, yeah, I didn't explain it on the slide. So, cat 1, who is unentangled, has nothing to do with cat 2. Suppose they both have this exact state. And what is the state of both of them? Well, obviously you could just describe it this way, but if you wanted to give the if you want to give the description in the sense we described earlier, remember what we said earlier was when you have multiple qubits, don't give, if you have like n qubits, don't give 2 times n different complex numbers, give 2 to the power of n complex numbers. Slightly confusing when n is 2 because like 4, this is 4 and this is also 4. So here I tried to use the example of, n not being 2, but what I mean is basically if you have like 2 cats in 2 boxes and you want to give the description of what they're doing, you could give, because they're a product state in this example we're discussing, you could say, okay, this one is in the state 1 over square root 2, 1 over square root 2, and so is this one. But what you should do if you want to okay, you could do that. But you could also, if you want to stay consistent with what I described here, and you want to explain a state on 2 qubits as a 4-dimensional vector, then the 4-dimensional vector would be half, 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 and half. And that's, where did I get that? That's just by taking the tensor products of, 1 over square root 2, 1 over square root 2, tensor. If you were to evaluate what this is, you would take this times this times this, and they're all the same, they're all half. Okay, so what I'm saying is you want to describe 2 qubits, give me 4 numbers. If you had 3 qubits, they're all quantum, quantum boxes of cats, and they had nothing to do with each other, then you would give me 8 numbers. And that would be 1 over square root 2, 1 over square root 2, like tensored with itself 3 times. Just maybe I'll just write that down so that it's absolutely clear. The state of these 3 cats would be this, this mathematical expression. And if you evaluated this, I haven't evaluated here, but if you did, you would get like 8 numbers. They would all be the same, but you would get 8 numbers. Okay, but because this is a product state, we don't have to evaluate it, and we can use these tensor products as like commas that separate the descriptions. But the whole point is there are entangled states too, and that's where quantum gets interesting, and it gets quantum. And there are some states like this one that you just simply cannot separate, and you just simply cannot say the first cat is doing this and the second cat is doing this. Okay, now I just want to give you some intuition for what this feels like. In this case, when you have these entangled cats, specifically these ones, these are 2 cats whose fates are sealed. When you open one box and you see that the cat is alive, the other box will necessarily have, an alive cat as well. And if you open one box and you see the cat is dead, the other box will necessarily have a dead cat in it as well. So this is the state that corresponds to maximum entanglement, 2 quantum bits that even they can be like separated in space. One, they can be on the other side of the universe. But the moment you measure one, you are certain about what the other one is doing. And that's kind of like, it doesn't rely on the speed of light at all. So it's like instantaneous, but you can't really use it to communicate. So don't get too excited about that. But yeah, absolutely. Like 2 quantum bits who are perfectly entangled, they will do what the other one is doing when you measure them. That is what this vector over here corresponds to. And now you know what entanglement means. So if you ever read a meme or something, I mean, some of you already probably knew it, but for those for whom it's new, now you know what it means. It's just the fact that you can't describe the state of these like 20 qubits by describing what each of them is doing. The only meaningful description is a combined description, which requires 2 to the power of 20 complex numbers, not 20 times 2 complex numbers, which is what would be the sort of naive expectation. Is that clear so far? I'm just going to assume that I'm explaining things so well that there are no questions. Okay, this is the final part of the mathematics, the final piece of the puzzle. Once you get this, you can start applying for jobs in quantum computing. I'm kidding, but I mean, you probably could, but you don't want one. By the end of this talk, you'll see why. So, okay, reversible transformations. Now, so far we just talked about how we can describe what a quantum state is up to and how we can measure it, but we haven't talked about transforming it, like doing computations, applying logic gates and that kind of thing. So that's what this next couple of slides is going to be about. And we're going to use a little bit of matrix, like, you know, matrix algebra kind of thing. So if you're not so familiar with that, I'm sorry, but maybe if, depending on what field you're in, like definitely learn about this. So, okay, what does quantum mechanics allow us to do? If we have a qubit, or we have a state of, we have some like 10 qubits or whatever, what quantum mechanics says is there exist these things called reversible transformations, okay? So we really emphasize the fact that they're reversible because firstly they are, so when you apply one of these, there is always a way to undo it. But they're also very different from the measurements, which were irreversible. Once you open the box, the cat is now either dead or alive, and you know, you can't just like unmeasure it. You could re-prepare the state, but you can't go back to what it exactly was before. Which matters in cases where you don't know what the state was. So suppose I send you a qubit, you don't know what the amplitudes are, and you measure it. Now you just get some outcome. You don't know what the amplitudes are still, right? So let's say I send you some qubit and it has like, I hope I got this right. So I send you this qubit, but you don't know I sent you this qubit. You just have some qubit. Oops, that's the same. Okay, so remember what this is. It's some two-level system, which has like this kind of quantum behavior. And the only way we can capture this behavior is by saying there's an amplitude of half corresponding to what it's doing at state 0, and an amplitude of square root of 3/2 corresponding to its being in state 1. And so that's what you don't know this. I prepare a state like this to send it to you. And then you're like, oh, let me see what I got. You open your present and you just get 0. There's no way to reverse that measurement. If you open the box again, it's still going to be 0. Right? So that's what I mean by measurements are not reversible. But there are these reversible transformations as well in quantum computing. And those are the things, and in quantum mechanics, and those are the things that we use to like do the circuit. What we'll see basically is that a quantum circuit is going to compose of, you know, initializing all your qubits to just some state, doesn't matter because you can change them later, doing some reversible transformations, and when you're done, performing some measurements upon these transformations to get your outcome. So we've talked about how this works. That was Born's rule, the squares of the amplitudes. We've talked about what it means to describe the states. Here we have a product state because it's just the beginning, but maybe at some point in our computation, we won't be able to describe what our qubits are doing by, you know, individually describing them. We would have to give a full description, or we will not be able to do that. Suppose we were, you know, programming a 1,000-qubit quantum computer. You're not going to be able to debug that by hand. You're not going to be able to debug that even using a classical computer too easily, right? But if you sort of, in principle, the full description would be 2 to the power of 1,000 different complex numbers. I'm repeating these things a lot, but hopefully that's like pedagogically helpful. So, okay, this is the general structure of how to do a quantum computation. Prepare your states, apply some reversible transformations, which we'll discuss in a second, and then measure your outcomes. So what are these reversible transformations? Well, they correspond to a very special type of matrix, a type of matrix that if you study linear algebra to maybe like a second course, you will already know of them. Unitary matrices, these are really important in linear algebra, even before like quantum mechanics was a thing. And they are matrices that have this property. Their conjugate transpose is their inverse. Okay, so this symbol is read as dagger. It's also sometimes read as adjoint, but there's another different thing in linear algebra called an adjoint, so that gets confusing. And I think the least confusing description is conjugate transpose, because you just explain what it does. So conjugate transpose of a matrix, if the conjugate transpose of a matrix is its inverse, you have a unitary matrix. So what does it mean? What does it mean to transpose a matrix? It means to like flip it along this axis. And what does it mean to take the conjugate of a matrix? It means to take the complex conjugate of each component. Okay, so if that's like really too fast for you, just think of it as a very special type of matrix that people are familiar with. If you've done math before, you should follow that. This is, we're doing a transpose. So let's look at this example. So how do you get from this matrix to its conjugate transpose? Well, actually the order of conjugate and transpose don't matter. So let's do the conjugate first. If we take the complex conjugates of these numbers, real numbers don't have complex parts, so we don't have to take the conjugate. For this one, to take the complex conjugate, we change the coefficient on the imaginary part. We take it's negative. So 1 minus I becomes 1 plus I, and then I becomes minus I, 1 becomes 1. So that's the conjugate part of it done. And then if we want to take the transpose, we have to flip it along this axis. So this number goes there, this number comes here, and you'll see that that's what we get over here. Okay. So again, this is one of the things I feel like for those who maybe got it, it was too slow, and if you didn't get it, maybe it was too fast. So maybe if someone feels like they're just on the cusp of getting it, or actually no, like if you didn't get it at all as well, like just please ask a question. We're almost done with the math. So if you're feeling like, oh, I don't want this to go on longer, like this is really almost the last slide already. So if you want to ask a math question now, you can take like a good amount of time with it. All right. So fine, it's a special type of matrix, unitary matrix. Its property to be a unitary matrix, you need to be a matrix whose inverse is your conjugate transpose. And basically what this means is you can't just use any matrix. You can't evolve. So if you have a qubit in the state 1 over square root 2, 1 over square root 2, and then you can't just build a quantum gate to do this operation. This is not a unitary matrix, right? And by the way, I'll just say, like, for those who again are very comfortable with math, another way of defining what a unitary matrix is that it's a matrix that preserves the length of the vector. And we need that because to be a quantum bit, you need to be not just a complex vector, but you need to be a complex vector whose length is 1. So any evolution we do on a quantum bit should preserve that property so that it's at least you still get a quantum bit out of the system. Okay, cool. Good stuff. Okay, so we now know what quantum mechanics allows us in terms of computation and in terms of transformation. There are these special types of matrices that we're allowed to build and perform as gates. And like physicists are amazing people, engineers are amazing people. For any matrix like this, they know how to do it. Okay. So now we can look at quantum gates. Like we can actually start building quantum computers in our minds, in terms of designing quantum computations because of all that we've discussed so far. So here are 2 very common gates, and these are the ones that you should, right now, just try to familiarize yourself with the most because we'll use them on one slide. You have the Hadamard gate and the C0 gate. Let's look at the C0 gate first. It's a bit easier. The C0 gate is kind of just the logic gate. It's a controlled NOT gate. So if the first input is 0, it does nothing because the control wire is off in a sense. And if the first bit, I'm going to describe it as bits first, and then I'll tell you how this comes to qubits. So if the first bit is 0, it does nothing. If the first bit is 1, then it acts like a NOT gate. So if you look at the truth table for it, when this is 0, nothing's happening in this section. It's just the identity. But when this is 1, it does a flip. 0 becomes 1 and 1 becomes 0. Now the thing is, we could have sent through some quantum states like this, and we could treat them as bits for now, right? And so you can think of C0 as the reason we call it C0 is because when you just send in very simple quantum states that are not in any kind of superposition. So let's just think about what this state is, right? So far, we've seen states which are like something plus something. But you could imagine that this coefficient, the first coefficient, is just like all of the amplitude. It's just 1. And the second coefficient is like 0. So this dies away. So this is the quantum state, of like an atom in its with electron and ground state, or a dead cat. It's just 100%. It's just a classical state, really. So C0, when acting on these very simple, non-superposition quantum states, acts like a bit of a logic gate, but we still use it when we send in like, these cool quantum states. So we can absolutely pass a state like this into, the C0 gate. And it's really cool to see what happens when you pass. In general, this is just a cool thing. When you pass like quantum states into regular classical circuits, what behavior they do is quite interesting. So this circuit actually outputs the maximally entangled state that we saw earlier, both cats being either dead or alive and their fates being sealed. Okay, and then we have the Hadamard gate. The Hadamard gate, so I don't know how much detail to go into, but basically it's fully characterized by these two properties. It's the gate that sends the 0 state to the state 0 plus 1 over square root of 2. So this is our familiar state from earlier, where we had, the cat being like amplitude 1 over square root 2 being alive and amplitude 1 over square root 2 being dead. And it sends a state 1 to this state. And this state has the same like probabilities. So if you think in terms of Schrodinger's cat, like there's no difference. But in terms of like quantum physics and like, more advanced quantum computations, this is a totally different state because it has the amplitude corresponding here to the state 1 is minus 1 over square root 2. So that's a different state. And, obviously when we get to more complex computations than just like preparing and measuring states, these things, they're called phases, start to matter much more. Okay, and by the way, this is how we draw it when we do quantum computing. This is how we draw Hadamard gates. It's a real field, like we have our own stuff. Okay, we haven't built it, but we have like good plans, solid plans, like probably gonna happen. And just, some other quantum gates, T gate, S gate, swap gate, poly X, poly Y, poly Z. These are the matrices corresponding to them. Pretty much most quantum computing operates using the gates I've presented so far. Okay. And you can see a swap gate is like, it's also a physical thing. Like you're literally moving one thing in one direction, like moving it, you're literally swapping the position of two things. But that can be written as this matrix. And I think that's pretty cool that like mathematics is so robust in general that, even when you describe simple things that have intuitive logic, that they fit into the system. They work as they should. And this is another important gate called the Toffoli gate. It's also like a bit of a logic gate. But yeah. So just to give you an idea, like when I'm doing quantum computing, like I did my thesis, I was playing around with these gates and seeing, what are the identities? How can I swap them around? How can I simplify circuits? Just like you might do in a digital logic course, how can you make like OR using only and not, this kind of thing. So we do the same stuff in quantum, but we have to multiply matrices. Actually, I didn't say that at all. Maybe I should say that. What you do when you pass a vector through a gate is you multiply that matrix. So if we had the state like 1, 0 going in through the Hadamard gate, the result over here would be this matrix H times 1, 0. So if you could write out the full thing. Times 1, 0. And if you evaluated what that is, it would be 1 over square root of 2. Okay. All good? We're done with the math, so.
Wait, when you multiply, right?
Yeah.
Like, I understand, like you multiply 2 times 2 with 2 times 1. Then what about the 4 times 4?
Great question. Yeah, nice. So when you have, so let's look at the Toffoli gate. The Toffoli gate acts on 3 qubits. Okay. So remember, we said we could write the state of 3 qubits as a product state, but not for all, for some of them. in general, the state of 3 qubits is going to be a how many dimensional vector? Pio?
Is it 8?
Yeah, 8. So it's 2 to the 3, and that's 8. Right? In general, if you have n qubits, it's 2 to the n dimensional vector. And if you count how many rows and columns there are on the Toffoli gate, it also has 8. So basically, like if you have a quantum gate on 10 qubits, that's going to be a massive matrix. It's not going to be, yeah.
Okay, got it. Yeah.
Any question? That was a good question. I'll just throw some trivia. The Toffoli gate is actually universal for classical computation. So it's like the NAND gate on its own. You can create any classical like logic circuit using just the Toffoli gate. Is there any other trivia? Yeah, that's fine. Okay. So now, look, I can't, it's just not possible to explain all this and then also give you a description of a very important quantum algorithm like Shor's algorithm. I mean, I would have to go through how RSA works, which would require some number theory. I'd have to go through like some group theory. So those are things you can learn in a week if you want to, but it just, I'm sorry, but there's just no way I can explain like a quantum algorithm, you know, in the very first lecture. But it's still possible for me to explain 2 very simple and meaningful quantum circuits. So we've seen them already, so it might feel a bit repetitive, but you can imagine from an operational perspective, you're building a quantum computer. So all quantum computers, we start with, you know, initialize all the states to like 0. We just put in the atom, we don't excite its you know, electron, or there's just a dead cat to begin. Okay, this analogy doesn't work anymore, but we just begin with the state 0. And this circuit here, this very simple circuit, does a coin flip. It first prepares the equal superposition state. So over here, our circuit would be in the state 1 over square root 2, 0, this 1 over square root 2, 1. We've seen this already. And then this box means measurement. So once we measure it, we're going to get one of these outcomes. Probability of 0 will be half, probability of 1 will be half. Now, let me tell you something. This might seem very simple. We already can do random numbers, but this is already a huge win for quantum computing because this is a genuinely random number, right? The random numbers you get from your computer are just sort of some hacks. They're like pseudo-random. They do some tricks that actually do have some patterns to them, but those patterns are very complex. And sometimes security protocols are broken because their randomness is broken. Someone figures out how the random keys are being generated and they're able to guess keys better. So this is a completely unguessable, unhackable randomness. This is like, you know, just with one quantum gate, we have a very important thing in computer science, genuine randomness that you cannot, you know, work out from before what it's going to do. And that's guaranteed by the laws of physics. So it's obviously laws of physics are always subject to change, but at least for this era of humanity, as far as we know, everything we know, this is a genuinely random coin flip, something you can't hack and start to exploit in a security protocol. So that's already a win for quantum computing. And there are, so, you know, if you're thinking about it from a business perspective, this is roughly why quantum networks and quantum security and quantum communication are an exciting field. This is why, you know, China especially has been investing so much into quantum networks. It's because you can have unhackable things like this. So many of the properties, we'll see some more, but so many properties of quantum are just so well suited to security, like this genuine randomness. Okay, here's another quick meaningful circuit. I keep saying maths is over, but you see maths is really over now, okay? So bell pair preparation. Again, we've seen the state before. This is the 2 cats whose fates are aligned. You can say the 2 atoms who either, you know, both have their electrons in the ground state, and the amplitude for that outcome is 1 over square root of 2, or both have their electrons in the excited state, and the amplitude corresponding to that outcome is 1 over square root of 2. And you can prepare this state by this circuit. So I mentioned it earlier. You take the Hadamard first on the first qubit, and then you take a C naught on both of them. Here we don't measure because the goal is to prepare this circuit. And by the way, this is also used in some security protocols. So what I might do, for example, is, I'll do this preparation. I'll create 2 qubits and I'll send one of them over a network, over a quantum network. And so now we will share, like me and Pio or whatever, we will share like entangled quantum bit wherever we are distributed in space. And we can use that. It ends up being useful in some security protocols, because only we have it, like the adversary won't have it. So we can do certain things that the adversary won't be able to participate in. Okay, cool. Any questions? All right, then let's get to the business end, which there's the part of the talk which is about like business matters. So what I really liked about like the first couple of quantum computing lectures I attended was we were just presented the model, just like how I presented to you. And I was like, wait, that's incredible. We can start dreaming about new types of algorithms, new types of data structures, new types of logic gates, all kinds of crazy things. Like, what can we do with this newly presented model of computation? Remember, before we had these bits, which are so lame, they can only be 0 or 1 in 2 different states. And you have like logic gates. But now we have like quantum bits, and they can have like, vectors of complex numbers, and they can be evolved by matrix multiplication. They can be entangled, and they have so much computational power. So what can we do with this? So here are the 3 things that we sort of certainly can do. And they're the kind of crowning jewels of quantum computing. The first one is, simulating physics and chemistry. There are, existing proposals. This was also what my thesis was about, just trying to make like very concrete proposals on how many qubits do you need, how many gates do you need to simulate some meaningful physical and chemistry stuff that classically has been intractable. Why has it been intractable? Because if you have some physical system, if the physical system itself you can imagine as being, let's say like 1,000 qubits arranged in some, you can imagine like some physical system is like modeled as a grid of qubits, and then they have like entanglements between them. Then just describing what this system is up to would be 2 to the power of 1,000 complex numbers, but we can do it, for cheap on a quantum computer because we can just use 1,000 qubits. Then the representation is native. We don't have to store the amplitudes. We can just model each quantum bit, and that's quantum systems can be more than just like 2-level. The ones you're modeling. So for example, it could be multiple like n levels, or it could even be some kind of real distributed thing. But there are ways to encode things that are quantum physical, quantum mechanical into quantum computers, which are more efficient than if you did the same thing and representing it in a classical computer using bits. Just because it's native, a lot of as I said, a quantum computer with 1,000 qubits has so much going on, 2 to the power of 1,000 complex amplitudes. So it's by no means trivial. There are still some like caveats here and there to be worked out. People are still trying to make it happen, but for the most part, we expect this to absolutely work. And then news articles will take that really far and say like, we'll make drugs, we'll program molecules and this kind of thing. Maybe that'll come, but we can do some interesting simulations. This is the thing that really makes you feel like, we went down the right path when we asked questions about quantum computing. Because if you have a list, like an array or some kind of list, and you want to search for some element in it, the element in question, say it's over here. What you do classically is you go over the list. Is it this one? Is it this one? Oh, okay, I found it. It's this one. The complexity of that is O(n). What that means is if the length of the list is n, you would take about n steps, right? In the worst case, you will take n steps to find this item because it could be right at the end of the list. So you have to go through everything. Or it could be like halfway through, but that would still, the time taken to find this would scale with the length of the list. If you had a very long list, it would take you longer to find something. Quantum computers also, obviously, if you have a longer list, it'll take you longer to find it. But the scaling is not linear. the scaling is square root of n because of this algorithm called Grover's algorithm. And that's just like that. If you've been studying computer science, that should make you go, what? Like, how is that even possible? And yeah, look up Grover's algorithm, spend maybe a day to try to understand it. You can generally search like a function. You can think it's easier because one of the questions you ask yourself is, how do you put a list on a quantum computer? Like, we're just got these like wires and things for now. But you can think of it as a function. So you have some function that, maps like a bunch of inputs to two different possible values, 0 or 1. And most of the things map to 0, but one of them maps to 1. That's the thing you're searching for. You want to know what that thing is. So how do you search this function? So you would implement this function in your quantum computer, and then you would run Grover's algorithm. And you would be able to find this thing not in linear time, but in the square root of n time. It just doesn't make sense the first time you hear about it. And another thing we can absolutely certainly do, and we have very like detailed proposals on the moment the quantum computer has been built, we'll be ready to like implement it, is Shor's algorithm, which factorizes integers in polynomial time. If you have like number 15, you can break that down to 5 times 3. That's not just something that'll help you with your math homework. That is like the basis of internet security, rests on the fact that it's easy to do this multiplication, but very hard to do it this way. Not for 15, but for giant numbers. It takes just computers far too long to factorize numbers. And this is like how it's called RSA cryptography. If this was cracked like today, the world would kind of go down for a bit. Bank like details would be hacked. Someone could impersonate Satoshi Nakamoto and claim all his Bitcoin. Like you couldn't send a secure email. Like everything would go down if someone hacked RSA today. Our internet security rests upon this assumption that it's difficult to factorize integers. And quantum computers came along, and quantum computer scientists came along and were like, hey, I found an algorithm to really efficiently factorize numbers into their primes. And that got people worried. And that's why I have a picture of a foot in the door here, because quantum computing was just a crazy idea until people came up with Shor's algorithm. Now it's like a government has to be paying attention to what's going on in the quantum space, because they want to be the first to build a quantum computer, because they want to be able to eavesdrop, and they don't want their secrets leaked, and they want to read other people's secrets. So it's become a national security issue. Quantum computing can't go away easily because one person called Peter Shor found this one algorithm to do something so significant, factorizing integers in polynomial time. And because of all the linear algebra we've seen involved, we expect that quantum computers might possibly be able to speed up linear algebra related computations. They might possibly be able to do some machine learning stuff, but the jury is still out on that. People are excited, and what's really cool, so Shor's algorithm, if I'm not wrong, came out in 1991. And the interest in quantum computing, so it's been 30 years. We have found new stuff in 30 years, but it's still like very, very early days. And what's really cool about this field is we need people to come in and find new algorithms, think in completely new ways. And it's a cool space because there's no one here, so you can, whatever you come and do, you can go on your own path, and that's really exciting. We talked a bit about quantum networks and communications. Here's another reason why quantum bits are exciting. Suppose you have some kind of optical fiber or some kind of communications link that allows you to send coherent qubits. What I mean by that is you can send the qubit unmeasured, like it goes through the whole wire without being measured at any point. I won't explain exact details, but you can't have an eavesdropper in a quantum setting because an eavesdropper would measure the qubit, right? And so the moment, let's say Alice sends Bob a qubit, and Bob starts to notice that he's receiving like measured qubits, which just, the idea is just that when Eve looks at the qubit, she has to change what the qubit is. So Bob's going to start to see some pattern if you create the protocol in the right way. So quantum physics is going to give us security with some physical guarantees, not just computational guarantees, which we are used to. For example, as I said, the world would come down if someone found a way to factorize integers into primes, right? We literally rest on a computational assumption, an assumption that certain things cannot be done fast and efficiently. But that's not a really good assumption, because you can't really, we haven't proven that. And so we just sort of assume that, you know, there's no way to do it because no one has found a way for so many years. With the physical assumption, it's totally different. This is not something, okay, physics could change as well, but physics is sort of, it feels harder to change than computer science, at least from my perspective. Yeah, you're not going to realize that, oh, actually, there is a way to eavesdrop on a quantum system that no one had figured out, as much as it seems possible to figure out a way to factorize numbers efficiently. So quantum really supports security natively, which is just really cool. Okay, I want to say, I know I'm exceeding time, so I'm sorry, but I think things are going well. I want to say that quantum computing is a speculative technology. Okay, so many people tell me, wow, quantum computing, that's like the next big thing. It's not really, because some next big thing technology, like machine learning, it's already being used. It already like makes money. You can start a machine learning company and be relatively sure you're going to deliver value and make money out of that. But quantum computing is still a dream. So to do useful quantum computations, we expect to need millions of qubits. So far, we've built systems with like 64 qubits. It's true that we haven't been trying for that long, and we expect to make progress. Google and IBM both want to build million qubit quantum computers by the end of the decade. There are some startups who make more spurious claims than that, and people don't really trust them. But they want to make million qubits even sooner than that. But Google and IBM, it's unclear. Some people say there's a lot of business pressure on them, so they say things like that. But yeah, it's on the agenda. If they're aiming for 1 million and they're investing all throughout the decade, we probably hit like 10,000, hopefully. But quantum computing is very much still a dream. People are trying really hard to make something out of the 64 qubits that already exist, but they are noisy qubits. They aren't exactly, the mathematics we described is like assuming they're perfect and they do exactly what you want them to do. But really what happens is that every time you do a gate, there's a 1% chance the qubit does something completely random that you didn't expect. So people are trying really hard to make something. It's called the NISQ era. You might see this if you read about quantum computing, the noisy intermediate scale quantum computers. And in the NISQ era, it's unclear if you can do anything meaningful, or we have to wait for building something called fault tolerant quantum computers, which basically means that we use some error correction schemes so that we use maybe like 50 to 100 or 1,000 qubits to actually represent just one qubit. And if there are any errors, we have like error correction schemes that make sure that those errors don't affect the computation. But that even complicates things further, because if we need like millions of qubits, I think that millions of qubits already assume we need the error correction. So yeah, why we need millions of qubits is not because there aren't cool circuits that you can do with 64 qubits. There absolutely are, but not with noisy ones. So to get rid of the noise, we need like hundreds or maybe even 1,000 qubits that all together represent one logical qubit. And you can think of this in the case of bits. So a very simple understanding of how your computer works is that instead of storing every bit, it stores like 3 copies of every bit. And so if one of them is like affected by some noise, like a I don't know, photon from the sun comes and hits your bit, then the computer can correct this. It said, oh, looks like one bit was flipped. Let me just undo it. So that's like a very naive description of how your computer's like error correction works within it. And we want to do something like that for quantum computing, especially because quantum computing is so new. We haven't worked out all the technology yet. And as I said, things need to be cooled down to very close to absolute zero to keep things like noise free. So I would say there are 3 big things. If you're following the quantum computing news, there are 3 things you should look out for. One is, how much progress is being made on actually building these machines. If you hear an announcement like Rigetti or IBM or IonQ has, unveiled a 128 qubit quantum computer, that is something to be excited about. But wait till 1 million for your, business value, I guess. If you want to demonstrate, the second thing we should look out for is demonstrating error correction. So we have proposals, but we haven't actually demonstrated a full error corrected qubit. What that would mean is we build a machine that stores a qubit, and this qubit can be left overnight in its state. Currently, we can't do that. Currently, we have like a few seconds at most. Really, it's like microseconds, milliseconds. So I think when you look at it, when you hear from experts in the field, they say that when this second milestone is reached, an actual experimental demonstration of quantum error correction, that is likely to win a Nobel Prize in physics. I don't know how that makes physicists feel, but that is something that people are saying. And finally, we need to find algorithms and applications. And I think most people here aren't hardware people. We are like, computer science type people. So absolutely, like, keep your ear to the ground. If you feel like something feels, maybe I could use quantum here, you find an algorithm, like that is something that will make you famous. If all the algorithms, like Dijkstra's algorithm or whatever, all these algorithms that have like people's names, Bellman-Ford algorithm, like that could be you, because those algorithms now are really simple. We learned them in high school and all kinds of things, but when people came up with them, it was like a big deal. No one had thought in that kind of way. And yeah, that's what's like really exciting about quantum computing. If you just find an algorithm, it seems like something that a young person who's motivated could do in a couple of years. That is a really good way to make a massive contribution to humanity, to push the agenda forward for quantum computing, to move towards like humanity that doesn't just use electricity, which is already very cool, to do computation, but can literally manipulate individual atoms in service of calculation, computation, trying to model the universe. And like computation and modeling universe is not the only value. Like, and I'm the last person to think that everything needs to be reduced to computation, but we have to give it credit. That is really pushing humanity forward. So I described that it's no fairy tale. Quantum computing is not like machine learning. But why do we like press on? It's really because of a lot of things I said. Maybe I'll leave this to discussion. I'll just discuss this last one, which is today you learned some quantum mechanics. Congratulations, like you spent your Saturday afternoon or whatever time zone you're in, like Saturday morning, learning some basics of quantum information, really some basics of quantum mechanics. I never thought I would get to quantum mechanics, to be honest. I'm always interested in like the foundations of things, but there were some things that I thought were just like requiring too much effort that I wouldn't actually go and do them, even though it would be cool to know, because it's like the fundamental theory of everything as far as we know, like the best theory that we know. But quantum mechanics, it uncovers, quantum computing uncovers quantum mechanics. It brings it to everyone. And you could imagine in a world where quantum computers are more common, everyone doing a computer science degree has to learn some quantum mechanics. And that just pushes humanity forward as well. In the way that today we all know about Boolean logic. I mean, Boolean logic was really like a branch of philosophy at some point. Not many people studied it. But because it's a big part of mathematics and computer science, it's been uncovered and disclosed to us, and we all learn Boolean logic and maybe even other types of logic. So I think this is one of the coolest things about quantum computing, apart from obviously the way it shakes up some of the assumptions in computer science. It adds new primitives to computer science. So we don't just have information transformation and these things. We have like entanglement and measurement and superposition, and we get to dream about what kind of cool computations we can do with that. And yeah, you can just maybe read that one yourself. So that's all I have, and I'm happy with how long I took. I think I'm sorry if you had plans later and maybe someone left quietly, but I'm glad now that you at least have a feeling for what people are talking about when they say qubit, when they say measurement, when they say quantum computation. And now we can talk, if you have questions like, how much investment is there in the field or something like that, like we can talk about all those things. I'm here to answer any questions. Thank you so much.